Good morning. Today we are going to discuss continuity of a function on an interval. So we start, that is continuity on an open interval. It means what's about the criteria to check the given function is continuous on that interval. Sometimes it is open, sometimes it is closed. So let's start with that is open interval. So any function, a function fx is said to be continuous on an open interval if it is continuous at every point on that interval. Any function fx is said to be continuous on an open interval, let it is ap, if it is continuous at every point on this interval. It means from that is in between a and b, so many points are there, and that function is continuous for all the points. Now continuity on a closed interval. A function denoted by fx is said to be continuous on closed interval ab if first one is it is continuous on open interval ab. Criteria number one is that should be the continuous on open interval ab. Second criteria, that is it is continuous at point, which point? This point. So at point A from right and at point B from left. These are two criteria, and second criteria can be characterized, that is from right. It means x tends to a from right, that is fx is equal to fa. And what is the meaning of at point B from left? It means that is limit x tends to b from left, means less, f of x is equal to fb. It means we have to check the continuity of that function in open interval ab, and we check the continuity of a function at point a from right and the continuity of that function at point b from left. So in this way we are able to show the given function is continuous on an open interval as well as closed interval. Now we are going to just discuss some properties. So properties of continuous functions. For the statement of these properties, we are required to take two functions. So let or if f and g be two functions, and that is always real. So be two real functions continuous at a real number, we can take that real number any c. Then first part is f plus g is continuous at point C. Second one is f minus g is continuous at x equal to c or at point C. Third one is f into g is continuous at point C. Fourth one is f divided by g is continuous at x equal to or at point C, provided g at C is not equal to 0. Next one is, that is, if f is continuous, then 1 by f is continuous at point C, provided that the value of the function f at C never equal to 0, otherwise it becomes undefined. Next property is, if f is continuous, then the mod of f is also continuous at point C. So these we can use directly, and I am going to prove first one and similar proof for other properties. So it is f plus g. So proof first one, f and g be continuous functions at x equal to c. It implies limit x tends to c, fx is equal to f of c. At the same time, limit x tends to c, that is gx equal to f of c. Now we start from, that is, limit x tends to c, that is the function f plus g. Now by the definition of a function, it may be written as limit x tends to c, that is f of x plus g of x. Now it can be written as, that is, limit x tends to c, that is fx plus limit x tends to c, that is gx. It implies f of c and plus g at c. Again, by the definition of a function, it may be written as f plus g at point C. So therefore f plus g is continuous at C. So this is the proof, and similar proof for other parts. Similarly, we will prove. Now we are going to deal with the functions everywhere continuous. So I start from here. Everywhere continuous functions. A function, similar definition, a function fx is said to be continuous continuous on what? Or we can say said to be everywhere continuous. What? Said to be everywhere continuous if it is continuous, if it is continuous on this is entire real line, that is minus infinity to plus infinity. This is the criteria to say that is a function is continuous everywhere. It means any function fx is said to be everywhere continuous if it is continuous on entire real line, or we can say it is continuous on whole set R of real numbers. Okay, now functions, that is starting from, that is constant functions, constant function, that is identity, polynomial, then sine function, cosine function, then exponential function e power x, a power x, then modulus function are everywhere continuous. At the same time, that is rational function, then tangent, cotangent, secant, then cosec, and that is logarithmic functions are continuous in their domains. It means I want to say if the function is defined for those numbers, then that is continuous. So some restrictions are there for these functions. For rational functions, denominator never be 0. For tan, again there comes cosine in denominator, that is not equal to 0. Same for cot, sec, cosec. For logarithmic function, same restriction is there, and that is using those restrictions, they are also continuous everywhere, and these are continuous everywhere. They are proved one by one, and in LMB theorem as well as Rolle's theorem, we directly use, if the function is polynomial function, then we say it is continuous everywhere. If a function is sine function, then we say it is continuous. Okay.